Good evening, students. Am I audible?
Yes, sir.
Yeah. So why is only 14 members present? Any idea about others joining or not? Is there any delay in school or something? Okay. So I just wanted to find out. See, I got some updates from one of the schools stating that you have exams starting from this week. So I know about behavior. I just wanted to find out about other students also. Arvind, are you there? Arvind? No response. Hello? Yeah, Arvind, can you speak? I'm not able to hear you. Okay, next. Narayan Murthy, are you there?
Yes, sir.
Yeah, when is your school exam starting?
Sir, for me, exam is going on, sir.
Okay. Okay.
And I'm, sir, another, sir. Sir, on 21st annual exam starts, sir.
So 21st is final exam, right?
Yes, yes, sir.
Oh, noted. Ramasubramaniam. Arvind, I want to know when is your final exam. Just tell me the dates, that's enough. Ram Subramaniam, you also the same thing. Okay, so I understand that mostly for you guys, by third week or by the end of this month, you have these final exams. Is that right? From 23rd of February. Okay. I get it. So listen, last week since I was not well, yeah, I had to upload certain videos from oscillations, and I checked the status. It is highly disappointing that most of you didn't do it, except few. But I made a list of those names whom I'll be contacting personally to find out the reason of why you have not worked upon it. So with respect to physics, there are two chapters that are left out. One is kinetic theory of gases, and the second is waves. Okay, so waves chapter, as I told you, it is very, very important for your next year physics as well. So we'll be starting with waves chapter. So one thing I would like to mention before I start is I cannot go in depth into this chapter. I'm only going to teach you from exam point of view because every school has a cramped schedule of this final exam. I didn't think that they'll conduct it so fast. Okay. So as of now, I'm going to start the chapter waves. I'll tell you. So this is the notes, okay, which is given to you. This is the study material of our academy. Right. I'm just explaining it from there only. So first, we need to understand what waves are. So if you see the previous chapter, we discussed about oscillations. So when I say about oscillation, it is something. It is a kind of motion where there is a to and fro option taking place with respect to an object about its mean position. So apart from to and fro motion, if there is a transfer of energy taking place, then that kind of a motion is called as wave motion. Okay. So first we need to understand what a wave is. Wave is basically a continuous disturbance. See, suppose there is a still water, right? So in the still water, if you're going to drop a stone, what is going to happen? You will have some circular disturbance that is crossed, that is created across the place where the stone is dropped, which we call it as ripples. Right? So this is what happens when you see it from the top view. So when you see it from the top view, you'll be able to see a set of concentric circles that are happening. Whereas when you see it from the bottom, that is when you see it from the side, what will happen is, you can see that the stone has gone inside and created a disturbance like this. So the stone would have actually created a disturbance, and this is how the disturbance would have transmitted energy from one place to another. That is what we technically call it as a wave in terms of physics. So basically, what is a wave? Wave is a continuous disturbance which transfers energy and information from one point to another without the actual transfer of matter as a whole. Okay, this is the first point. So water waves are familiar examples. So when a pebble is dropped into a pond, it disturbs the surface of water. Ripples of the surface of the pond travel away from the spot where the pebble landed. So this is the basic definition of wave. Is there any doubt in this?
No, sir.
Okay. Now, so we are going to see the types of waves that are existing. So when you talk about the types of waves, basically the classification takes place on whether a medium is required or not. Okay. So based on whether a medium is required or not, they are classified as three types. One is mechanical waves. So mechanical waves are those waves which need a material medium for propagation. The example you can think of is water waves, sound waves, seismic waves, and all these things require a material medium for propagation. Whereas when you talk about non-mechanical, which are also electromagnetic waves, they do not require any medium to propagate and hence can propagate through vacuum. Example is light waves, radio waves, X-rays, microwaves, and all these things. So electromagnetic waves are basically nothing. You would have heard of the word electromagnetic spectrum. In that electromagnetic spectrum, it comprises of light waves, radio waves, X-rays, microwaves, etc. Similarly, you have something called as matter waves. So they exist within the matter as they are associated with the fundamental particles of matter like electrons, protons, neutrons, etc., even atoms and molecules. So matter waves, for this year, it is not a very big concern. Matter waves means, to put it in simple terms, there is something called as dual nature of matter. In the dual nature of matter, what happens is, we know that electron revolves around the orbit in a circular path, but electron, along with revolution, it also has a wave-like structure that is formed, and that wave-like structure which it is having is what we call it as matter waves. And we will be discussing about this in depth in next year. So as of now, concentrate strongly on mechanical and non-mechanical waves. So how are they classified? These waves are classified on the basis of requirement of medium. If a medium is required, it is mechanical wave. If a medium is not required, it is a non-mechanical wave. Okay. So having said this, we will see the next type of classification that is going to happen, which is called as transverse and longitudinal waves. Okay. So transverse generally means perpendicular. Longitudinal generally means along the length. Okay, try to understand this. So there are two things to be taken into consideration. The direction of vibration. So you take the direction of vibration and the direction of propagation. So when you take these two things, right? So if the direction of vibration and the direction of propagation are perpendicular to each other, I repeat it, listen to this carefully. If the direction of vibration and the direction of propagation are perpendicular to each other, then we call it as transverse waves. Similarly, if the direction of vibration and propagation are along the same angle, if they are at the same angle, either at 0 degrees or 180 degrees, then you call them as longitudinal waves. So the best example for transverse wave is again electromagnetic waves. So electromagnetic waves is nothing but light. Light is a transverse wave in nature. Longitudinal waves, the best example is sound waves and water waves. So these are all longitudinal waves. Is that clear, guys? Any doubt till this point?
Yes, sir.
Clear? Okay. So proceeding to the next part. So let me read out this point. These are the waves in which the individual particles of the medium oscillate perpendicular to the direction of wave propagation. That is transverse wave. So for transverse wave to be understood, we will consider a horizontal string, because this is important for me to explain how the equations are written. So if you consider a horizontal string, you know what is a horizontal string? You take a string, you think of an electric guitar, right? So it will be tied at both the ends. So that is the example of a horizontal string. With one of, so in this horizontal string, what we are doing is we are keeping one of the ends fixed to a rigid support and the other end held in the hand. If we give its free end an upward jerk, so if you give it an upward jerk, something like this, an upward pulse is created. So what happens is the particle at this point gets raised like this, and it will transfer the energy to the subsequent particle, so that you will be able to see a bump like this, and that bump is what is called as an pulse. And if the pulse is in upward direction, we call it as an upward pulse. Okay, then what will happen is this upward pulse is there which travels along the string towards the fixed end. Okay, so each part of the string, that is when you take the other part of the string also, successively undergoes this disturbance about its mean position. So when this is happening, right, when each part of the string undergoes a disturbance about its mean position. So this kind of a thing, a pulse is created when you vibrate it once and leave it. But if you do the same process continuously, then what will happen is you are giving up and down jerks to the free end of the string, and you are able to see a sinusoidal wave like this. And this sinusoidal wave is what is called as transverse wave in this context, because the particle, the string particle, is vibrating in this direction. Okay, but the energy is getting transmitted in this direction. So the direction of propagation and the direction of propagation and the direction of vibration of particles, they both are perpendicular to each other. So as a result of which, this is what is an example. So the wave that is created on a string through continuous vibration is an example of transverse wave. So if you see all the musical instruments, right, stringed musical instruments, they work on the principle of transverse wave only. So is that clear, guys? Is it clear or not?
Yes.
Yes. So generally, when you talk about a transverse wave, it travels in the form of crest and trough. Okay. So the point CC of maximum displacement in the upward direction are called as crests, and the points T, T, so on till maximum displacement in the downward direction are called as troughs. So one crest and one trough put together is what is going to be one wave. Means one crest and one trough put together will give you one wave. Similarly, if I take from here, this is okay. I'll take another color. Similarly, if I take it from here till here, this is another wave. Third, it keeps on going like this. Okay, but remember, this is a transverse wave. Okay. The next topic that we need to discuss about is a longitudinal wave. So when you talk about a longitudinal wave, these are the waves in which the individual particles of the medium oscillate along the direction of wave propagation. Means the wave propagation and the direction of vibration of particles are along the same direction. They can either be at 0 degrees or 180 degrees. Okay. So what you need to do is consider a long hollow cylinder AB. So you consider a long hollow cylinder AB. You can think of a PVC pipe. Okay. Having a movable piston at one end. Okay, they took this thing. Long hollow cylinder. So you have a movable piston at the other end. If we suddenly move the piston rapidly towards right, if you move the piston rapidly towards right, what will happen is there is air filled inside. Then a small layer of air which is in contact with the piston head is getting compressed. Right? Is getting compressed. This layer moves towards rise, and what will it try to do? It is getting more amount of energy stored in it, so it cannot hold it. So what it will do is it will transfer this compression status with the energy that it has. It will try to compress the successive layer. That is what they're trying to say. This layer moves towards right and compresses the next layer, and soon the compression reaches the other end. Now the piston is suddenly moved towards left. The layer adjacent to it is rarefied. I'll tell you what is rarefied, resulting in the fall of pressure. Okay, generally, when you talk about compression, when something is compressed, right, you're trying to increase the pressure. When something is called as rarefaction, you're actually increasing the pressure. Just give me a minute. Listen. So there is a compression taking place, right? Then that compression is the place where the pressure is going to get increased. Pressure is increased. And there is something called as rarefaction, where the pressure is decreased. So when a transverse wave is traveling in the form of crest and trough, a longitudinal wave will travel in the form of compression and rarefaction. Okay, this is an important point that you need to know. So you're able to see? So compression is where the air molecules come together closer. Rarefaction is a place where the air molecules are away from each other, where the pressure is less. So are you able to understand why is this happening? It is because you created a disturbance on one of the sides with the help of a piston. Okay, so if you're able to continuously push and pull the piston in a simple harmonic manner, then what will happen is a sinusoidal sound wave travels along the cylinder in the form of alternating compressions and rarefactions. So here I would like to clarify one important point. So sinusoidal means generally you will start thinking that sine wave looks something like this. But here when I talk about longitudinal wave, there is no shape of this format. Whenever this format shape comes into picture, you talk about crest and trough. That is in terms of physics. Whereas the same shape in terms of mathematics is a sinusoidal wave. So are you able to understand what I'm trying to say? So why we are using the word sinusoidal sound wave here is because we will take the help of mathematical function. We'll take the help of sine function to write the equation for a wave which is traveling in the form of longitudinal as well, because still it is a wave. So for any wave in this world, the best mathematical term you can take into consideration is a sine wave or a cosine wave. Both the waves put together is what is called as a sinusoidal. Okay. So is it clear, guys? So these are the very important basics that you need to understand. Is it clear? Any doubt?
Sir.
Tell me.
Sir, I just joined. Could you summarize what we were doing?
I'm explaining about the basics of waves. Who's this who joined now? Yeah. Srigiridhar, okay. I was just explaining the basic. Okay. Some important terms connected with, some important terms connected with wave motion. So what are the important terms that are connected to wave motion? So when you talk about oscillatory motion, I would have told you there are certain terms associated with it. What was it? Amplitude, time period, frequency, and all these things were existing, right? Whereas when you talk about wave motion, wave is basically what? Wave is a combination of disturbance plus propagation. That is, wave is a combination of, instead of saying disturbance, I can say vibration plus propagation. Please understand this. So here when I say the particle is vibrating in a simple harmonic motion. When it is propagating, it is transmitting the energy. So try to understand this. So when I talk about wave motion, the most important parameter that needs to get associated with wave is wavelength. If you go revisit and see oscillation, right? In oscillation chapter, we would have never used the term wavelength because oscillations are not waves. Oscillation is taking about a fixed position and energy is not transmitted from one place to another. Whereas in the case of wave, what is happening? Along with the vibration, there is an energy that is getting transmitted from one place to another. So what is wavelength basically? Wavelength is a distance traveled by the wave during the time any particle of the medium completes one vibration. To put it in very simple terms, it is basically the distance between two successive crests or two successive troughs. Or I can say it is the distance between two successive compressions or two successive rarefactions. Even more simplest way to define it is the length of one wave. Okay. So this is what is called as wave length. Next is frequency. Please tell me.
Sir, one wave consists of one crest and trough, right?
Yes, one crest and one trough. Yes, correct.
Yeah, then how can it be like it's
Distance
wavelength?
between two successive crests, listen. It is the distance between two successive crests. If I take this point and this point, if I measure the distance between these 2 points, that will give me one wavelength. If I take two successive troughs, I didn't say between any two troughs, two successive ones is what is called as one wavelength. So that is the meaning. You're able to understand now?
Yes.
So the distance between two successive crests or two successive troughs is what is called as wavelength. Or the book definition says something like this. What is it saying? We may also define wavelength as the distance between any two nearest points of the medium vibrating the same phase. Meaning of it is, this is a point and this is another point which are vibrating in the same phase. So if I take the distance between these 2 points, that is one wavelength. So if I take a particle here, I will take a corresponding particle here. The distance between these 2 particles is also one wavelength. That is the meaning of that statement. So
Okay.
phase means a particular angle. So frequency, it is a number of vibrations that is taking, number of vibrations, or I can say number of oscillations that is completed by particle in 1 second. So frequency, you can define it as 1 divided by 1 divided by time period. Basically, it is the reciprocal of time period or the number of oscillations per unit time. So the SI unit of frequency is hertz. Similarly, when you talk about time period, the time taken by particle to complete one wavelength, or the time taken, so the time taken by the wave to travel a distance equal to one wavelength is what is called as time period. Meaning of this is very simple. Okay, listen to this. If I take a sinusoidal wave, from here to here, if I say the distance is one wavelength, the corresponding time it takes for this one wavelength distance to be traveled is one time period. Are you able to understand? Lambda t. Now listen to this. Amplitude, it is the maximum displacement of the vibrating particle from its equilibrium position. This is amplitude and this is also amplitude. This word you would have definitely seen it in the previous chapter as well. It's the same logic again. Okay. So the new term that you would be seeing is something called as wave velocity, which is also called as phase velocity. So that is, you're trying to calculate the velocity of the wave. So the velocity with which the disturbance or planes of equal phase. So don't worry about this wavefront. Okay. So the velocity with which the disturbance travels through the medium is what is called as wave or phase velocity. Okay. So time taken by the wave to travel a distance equal to one wavelength. Okay, listen to this. Is there any, sorry, I'm with wave velocity, right? Yeah. It is a velocity with which the disturbance travels through the medium. So how do you define wave velocity as? It is defined as the amount of distance traveled per unit time. Generally, speed is distance per unit time. Distance is wavelength. Time is one time period. So lambda divided by t is going to give us wave velocity. So this is the relation between wave velocity, frequency, and wavelength. Okay. Then there is something called as angular wave number or propagation constant. Listen to this. So before that, let me explain what is wave number. Wave number is not a new term. You would have learned this in your chemistry as well. So what is wave number? It is a reciprocal of wavelength, or I can say the distance traveled. Okay, I'll make it simple. It is a reciprocal of wavelength. Okay. Wave number generally is represented with nu with a bar on top of it, which I can call it as 1 by lambda, because it is reciprocal of wavelength. So have this in your mind, and the SI unit for this is meter inverse. Now listen to this carefully, guys. There is something called as angular wave number. So here it is wave number, here it is angular wave number. So whenever in physics, right, you have a prefix called angular to a particular quantity, then you need to multiply that quantity. Here the quantity is wave number. with a 2 pi. I repeat it. If you have wave number is what? Reciprocal of wavelength. Then what is angular wave number? If the prefix angular comes into picture, then you need to multiply the quantity with a 2 pi radian. When you do that, you get 2 pi divided by lambda or 2 pi into nu bar. Okay, and that is what is called as angular wave number, or more commonly called as a propagation constant. Listen to this carefully. It is called as a propagation constant. Okay. Is that clear, guys? Any doubt? These terms are very important. Any doubt, get it clarified, please.
Yes, sir.
Okay. Next is progressive waves. So when I talk about a progressive wave, this is also called as a traveling wave. So let me explain what it is. Generally, a wave that travels from one point of the medium to another is what is called as a progressive wave. A progressive wave may be transverse or longitudinal in nature. Okay. Now, the important point that we need to know, this is where the mathematical part starts. Everybody please concentrate. That is the displacement relation in a progressive wave. Right to understand, it's a displacement relation in a progressive wave. So if I ask you, what is the displacement equation of a particle in oscillation? So you would have written, right, y is equal to, anybody? Those who have gone through the videos last week, you would understand what I'm asking.
Sir, with respect to time or space?
It with respect to time.
Sir,
E
A
cos
sin omega t.
A, is that right? Correct. A sin omega t. Sometimes you write it as A sin omega t plus something called as phi naught. Am I right? What is that phi naught called as? It has a name. If you refer your notes, you will get the answer for it.
Epoch.
It's called as epoch, or you call it as initial phase also. Initial phase means initial angle, right? So if somebody asks, so if you look at this kind of an expression, y is equal to A sin omega t plus phi, can I do the reverse analysis and say that you will be able to understand that there is an equation for a particle strictly in oscillation? Correct? Can I say that? But here comes the question. Displacement reaction in a progressive wave, meaning is, when I use the word wave itself, what are the things that should come to your mind? It is a disturbance where the particles are oscillating and traveling. Correct? When that is happening, then I'm clear with the fact that the particle definitely has a parameter called as amplitude associated with it. Right? Amplitude is associated in the y direction, and it has a parameter called as wavelength that is associated along x direction. Apart from that, if I take a random point P which is x comma y, listen to this carefully. If I take a random point P which is x comma y, where y is the displacement of the particle in y direction and x is the displacement of the particle, obviously the x direction, then here if you see, in simple harmonic motion, y was only a function of time. Means the displacement of the particle either in y direction or in x direction was only a function of time. Whereas in the case of a plane progressive wave, the displacement of the particle in y direction is a function of two important parameters. So y is the displacement of the particle in y direction. Am I clear? So it is a function of two parameters. What are the two parameters? One is the displacement along x direction, and the second is time. So that is why if you see y of x comma t is written as A sin of omega t minus kx. This is written as y is equal to A sin of omega t minus kx. So look at the difference, no? For simple harmonic motion, you people told me y of t is equal to a sine of omega t. Basic equation. Forget about epoch. Forget about the initial phase. It is a sine omega t. Whereas in the case of the displacement relation for a plane progressive wave, what is going to happen? Y will be a function of both the displacement along x direction and the time. Is it clear? It is a sine of omega t minus x. Clear? Okay. Now I want to stress on some important. I'm not going to into the derivation, which is not much important. Okay. Listen. Here, the facts that you need to know is the minus sign is there, right? The negative sign indicates. Please write this point. The negative sign indicates that the wave is progressing in positive x direction. Okay, that is how it is derived. So this derivation is based on the concept of shifting of origin and all. So you need not worry much about it. Okay. Okay, so the point here is you need to make a note that if there is a negative sign existing between omega t and kx, then the wave is traveling along the positive x direction. Similarly, there is another equation that you'll be seeing in the next class, that is a sine of omega t plus kx. So here the plus sign indicates, what positive sign indicates wave is progressing in negative x direction. So this is a very important point. Have this in your mind. This is very important when you're solving problems.
Oh, so,
Tell me.
sir, but how do we draw a graph of with respect to the displacement and time?
This is the graph. This is the graph.
So, but
So
where is the
basically,
time
what
axis?
you don't need it. You don't need that. Okay. So what they would have done is, I'll tell you a simple logic, see if you're able to understand. I'll just give you a simple outline. Don't think too much about it. Just a minute. My pencil is not writing. Yeah. So if I take a wave like this, okay. So I'm drawing a graph showing the variation of y versus x. Okay. Now, if I take this angle as 0, tell me in radians, if this is a sine graph, this is going to be pi by 2, then how much is this angle?
Pi.
How much is this angle?
3 pi by 2.
And the last point is 2 pi. You're completing one full revolution. Is it right? Right. You listen to this carefully. I wrote in terms of x. But here I took the help of mathematics to write the angle in terms of radians. Correct? Now what I will do is, I will take any 2 points and I will say the distance between those 2 points is wavelength. So distance between 2 points is wavelength. Correct? Then phase difference between the 2 points that you have considered is how much? What is the phase difference between the 2 points that we have considered?
0, sir.
The phase difference, huh? This angle is 0, this angle is 2 pi.
2 pi.
No, it is 2 pi minus 0, that is 2 pi, no? Similarly, if I take, what is the time difference between 2 points we have considered? It is one time period. You're able to understand? You're able
Yes,
to
sir.
understand what I'm trying to say. So, in a similar way, can I frame, you know what is the unitary equation? So, like let's say one book costs 10 rupees, two books cost how much, means you can tell the answer, right? In a similar way, if I say one wavelength is crossed by a wave, then can I say that there is a definite value of 2 pi radian existing between those two phase values, which is so one wavelength distance covered by the wave is equivalent to 2 pi radians covered by a sine wave is equivalent to one time period. Can I say something like this?
Yes, sir.
Right. But what is the graph that you drew? Is it not the graph between y and x, but still you're able to relate it between time and other parameters? That is how it is released. So that is why they wrote here as t minus x by v. You're able to understand? So that is how they related it. So one of the major
Understood,
reasons
sir.
why I told you will not get into the derivation is it will start confusing you. Because time is also less, right? Or else I would have definitely taught in detail. Okay, as of now, accepted. So y of x comma t is equal to a sine of omega t minus kx. Okay, where a stands for what? Obviously the amplitude. Y stands for the displacement of the particle along y direction. And omega stands for what? It is the angular frequency. T stands for the time. K stands for what? The angular wave number. X stands for what? The position of the particle along x direction. And phi naught represents the initial phase angle. So this is a more generic equation. Y of x comma t is equal to a sine of omega t minus kx plus phi. It is not necessarily always plus phi naught needs to exist. Phi naught can be positive or negative. When you see problems, you'll understand it. Okay. So, but here, what is the important point you need to concentrate upon? What is the sign that is existing between omega t and kx? If the sign that is existing between these two parameters is negative, what did I tell? You need to conclude that the wave is traveling along the
Positive x direction.
positive x direction. Never forget this, okay? No. One minute. So the next topic according to your syllabus is 1 minute. So wave motion, transverse and longitudinal waves we have completed. Speed of traveling wave, displacement relation for okay. So this is done. So speed of traveling wave. Yeah. So next is we need to calculate the speed of transverse wave in a stretched string. Okay. Let's say you have a string which is stretched. So the meaning of stretched is it is having enough tension. Okay, you cannot observe the wave clearly, the string is without tension. That is why when you see the musical instruments also, right, especially the string musical instrument, they keep tightening the string so that the enough amount of vibration is produced in it. Or else what will happen when you try to plug that string, no vibration you can observe. So that is why you need a stretched string. So the speed of any mechanical wave, transverse wave or longitudinal wave, listen to this carefully, okay? It is according to the observation, it is observed that it depends on two important properties of a material. One is called as the inertial property of the medium and the second is called as the elastic property of that medium. Okay. So what is it? You take any type of a traveling wave. I repeat it. You take any type of a traveling wave. When I say something is traveling, it has a velocity associated with it. for those kind of waves, the speed of the wave is dependent on two important properties. And what are those two properties? One is the inertial property and the second is the elastic property of the medium. So the inertial property of the medium is the one which is responsible for storing kinetic energy. And the elastic property of the medium is the one which is responsible to store potential energy. Okay. So if you take a string, so what is the topic? Speed of a transverse wave in a stretched string. Right? When you talk about the speed of a transverse wave in a stretched string, it is derived like this. Let's not go with this derivation. Okay, it is derived like this. V is directly proportional to the inertial property raised to the power A and the elastic property raised to the power B. Okay, listen. This is by using dimensional analysis. Now, V is directly proportional to, now the important question that arises is, when you talk about a string, right, a string, with respect to a string, what is the inertial property you can talk about? What defines the inertia of a string? Guys, at least guess it.
Will be at rest.
No, inertial property means what? It is, see, inertia means what? Inertia is a property of an object to stay at rest or in continuous motion unless and until there is an external force applied on it.
It's displacement with respect to the mean position.
With respect to a string, what does it have?
It resists.
It is the mass. String has a mass associated with it, right? So a string has a mass and length associated with it, right? So I'm revisiting the topic. What did I say? You talk about the speed of any mechanical wave, transverse wave, longitudinal wave. It depends only on two parameters. What are they? One is the elastic property. One is the elastic property and the second is the inertial property. Elastic property with respect to a string is mass per unit length, which is called as mu. What is it? The amount of mass per unit length. It is called as linear mass density or mu. So what I'm trying to say is V is directly proportional to mu power A, and the elastic property of the string is defined by the tension which is present in it, T power B. Okay, so V is equal to some K times mu power A. What is mu, guys? T power B. What is mu? It is a linear mass density, or we call it as mass per unit length. So the dimensional formula of V is equal to the dimensional formula of mu raised to the power A and the dimensional formula of T raised to the power B. So what is the dimensional formula of V? It is LT minus 1 is equal to, mu is what? Mu is measured in mass per unit length. So ML minus 1 to the power A, and T is measured in what? T is force. So how do you define force as? Mass into acceleration, LT minus 2 to the power B. So what happens? M power A plus B into L power minus A plus B into T power minus 2B is equal to LT minus 1. So I can compare and say A plus B is 0, minus A plus B is 1, and minus 2B is equal to minus 1. So B will be equal to half and A will be equal to minus half. So what I can say is V will be equal to K into mu power minus half into T power half, which implies V will be equal to K into root of T divided by mu. K into root of T divided by mu, and K is observed to be equal to 1. So V will be equal to square root of T divided by mu. It is equal to root of T divided by mu. I suggest everybody to write this.
And why is k equal to 1?
It is experimentally found out. And this derivation will also show that you don't have any constant that is associated. Okay, this is slightly complicated, which I didn't want to go with. This is the one it is accepted in your school exams also, the dimensional analysis.
Sir, what is mass per unit length?
It's called linear mass density. Done? Right. This is the speed of what? This is the speed of transverse wave in a string. Okay. Now listen. Now the next one is, so from here, I would like to conclude one important point. So whether you talk about the speed of wave and any of the speed of any traveling wave that you want, then V will be equal to square root of elastic property divided by inertial property. So this is what happens. Please make a note of it. V will be equal to square root of elastic property divided by the inertial property. So that is why if you see in the case of a string, it became square root of t divided by mu. Whereas when you talk about the speed of longitudinal sound waves, then the speed of sound will be equal to square root of the elastic property of the medium divided by the density of the medium. Okay. So E stands for elastic property and rho stands for density. So in the case of, listen to this very carefully, okay? So in the case of string, the inertial property that comes into existence is the mass per unit length. Whereas in the case of longitudinal wave, it is the density of the medium that comes into existence. Okay, so it's called as Newton's formula. So according to Newton's formula, velocity of longitudinal wave in a medium is defined as square root of E divided by rho, where E is the elastic coefficient of the medium and rho is the density of the medium. So if you talk about the speed of the sound wave in a solid medium, the elastic property is defined by the Young's modulus. So velocity of sound in solid will be square root of the Young's modulus divided by the density of that material. Okay, so that is why if you see the velocity of sound in iron is 5,150 meters per second, which is very, very high. Similarly, when you talk about the same speed of sound in a liquid medium, who defines the elastic property? It is the bulk modulus. So bulk modulus divided by rho is what is going to be the speed of the sound in a liquid medium. If you take water, right, you apply the bulk modulus of water and the density of water, you can find out that the speed of the sound in water is 1,450 meters per second. Similarly, if you take a gas medium, okay, then what will happen is the velocity. So this is the important point. Concentrate again. The formula for velocity of sound in air was first obtained by Newton. So when Newton did this experiment, he assumed that the sound propagates through air at constant temperature. Means he assumed that sound propagates through a medium under isothermal conditions. Okay. So assume that sound propagates through a medium, through the air medium under isothermal conditions. So under isothermal condition, what happens is, so listen, velocity of sound in a gas medium is given as square root of pressure divided by density, where pressure is the elastic property of the material and rho is the inertial property of that material. Listen. So under isothermal conditions, guys. So Newton's formula. So when I talk about Newton's formula, it was derived under isothermal conditions. So under isothermal condition, we know that PV is equal to constant. So if I differentiate on both the sides, I get P into dV plus V into dP is equal to 0 because the derivative of constant is a 0. I applied the UV rule here. So P is equal to minus dP into V divided by dV. So I can write this as minus dP divided by dV by V, because if the V comes to the denominator, it will come like this. So minus dP divided by dV by V is nothing but the bulk modulus according to the definition in elasticity chapter that we saw. So under isothermal conditions, what is happening? The bulk modulus is mathematically equal to pressure, and we know that V is equal to square root of P divided by rho. In the place of P, you are going to replace it with bulk modulus and divide it with the density of the medium. Okay. So please make a note of this point. Right. So based on this, if you try to derive the value of speed of light in air medium, it comes out to be 279 meters per second. Okay. According to whose formula? According to the formula of root of B divided by rho. If you calculate the speed of sound in air medium, it comes out to be 279 meters per second. But in the later stage, it was experimentally observed that the speed of sound in air medium was not 279, rather it was somewhere around 330 to 335. So here it is given as 332 meters per second, which is much higher than the Newton's formula. So for that, what happened is, there was another scientist who proposed another formula, which was called as Laplace correction. I'll just give you the outline and close it. So the Laplace correction, what he did is, the small changes, Newton assumed that the sound propagates through air under isothermal conditions, but Laplace suggested that it doesn't travel under isothermal condition, rather it travels under adiabatic condition. So with that adiabatic condition, we will try to derive the equation which is given here. Okay, so this part I will derive it tomorrow, and I'll go to the next important concept, which is called as standing waves. Okay, tomorrow also the class will be at the same time. Right. For the next 2 days, it is going to be at the same time. I'll try to complete this chapter within the next 2 days and give it. Okay. So that's it from my side, guys. Any doubts? Any doubts?
Clear, sir.
Clear? Okay. Then we can wind up.